Hi everyone, I'm Eduardo Zannoni, the Vice President of the International Geosynthetics Society. It's an honor for me today to moderate the first lecture on the IGS 40th anniversary, and it's even more honor for me to actually moderate Jorge, which I met him. I'm very close to Jorge because we met somewhere in Africa, and I was in Mozambique. He reached out to me, and we've been talking about being influential. You want to know someone influential geosynthetic? You have it. That's Jorge. He chases me, and he wants a few slides because I show some geosynthetics somewhere in Africa. And 15 years later, that's where I am. So I have to thank him for showing me what IGS is and what the beautiful people and what marvelous solution is about. Anyway, I don't want to take too much time on the introduction, so I just want to start introducing Professor Zornberg. Has over 35 years of experience in practice and research in geotechnical and geosynthetic engineering. His research focuses on transportation geotechniques, geosynthetics, unsaturated soils, expensive clays, and environmental geotechniques. He served as the president of the International Geosynthetics Society, and he has authored over 500 technical publications, written several book chapters, and been awarded 3 patents. Professor Zornberg received numerous prestigious awards, including the Presidential Early Career Award for Scientists and Engineers, awarded by the President of the United States. The IGS recently established the Zornberg Lecture, an honorary lecture recognizing his contribution to the geosynthetic discipline. Hogan, with no further ado, I would like to give you the floor on presenting the power beyond learning geosynthetics. Please remind that the session is recorded so we can share it with who was not able. It's going to take about between 45 to 50 minutes. Please use the Q&A and we will have it at the end of the presentation. Jorge, the floor is yours. Thank you.
Thank you so much, Eduardo, for this introduction. And thank you also, Eduardo, for having initiated the first Ask the Officer program in which the IGS is interacting with you, the IGS member. As a past president of the IGS, I can tell you one thing. The IGS is in excellent hands, and I'm so proud of the work that the current leadership of the IGS, of their work that they are doing. So, but today, just because I'm a professor, I'm going to be talking about learning geosynthetics, and I'm going to be talking about teaching geosynthetics. Education is a core purpose of the IGS, education of geosynthetics, and I'm going to share with you some thoughts about this. So let's start talking about education on geosynthetics. And first, I'm going to start by telling you something that is a little bit obvious. So education on geosynthetics involves both learning geosynthetics and teaching geosynthetics. Now, the reason that I'm clarifying, making this statement of something that is reasonably obvious is because even though I want to convey some thoughts about learning geosynthetics, I will start by telling you a lot of the thinking that went into teaching geosynthetics first. So I would say that proper teaching of geosynthetics requires a good understanding first of the audience that you are talking to, the background of the audience that you're talking, and that is well known. As an educator, you know that you need to know the audience, but I'm going to tell you 2 aspects that are not necessarily obvious. One is that as to teach geosynthetics or any other subject matter, it's important to recognize what are the unique challenges of teaching, in this case, geosynthetics. And a third aspect, we need to be able to recognize what are the unique appeals of teaching the subject matter in this case, geosynthetics. So within the context of the audience background, I'm going to come back to what is the background, whether you're talking to initial or early exposure to geosynthetics or advanced exposure to geosynthetics. I'm going to focus primarily today about two aspects: the unique challenge and the unique appeal of geosynthetics when it comes to learning about geosynthetics. Let me start with the first one: a challenge in teaching geosynthetics. And I consider that an important challenge is their breadth. What I mean by this? Well, let me tell you about first, backtrack and tell you about early education on geosynthetics before I tell you about the challenge that the breadth, which is a very important aspect. It's a good aspect, but it makes the teaching challenging. Let me step back and talk about early education on geosynthetics, more specifically about education on geosynthetics to engineers at the college level, at the undergraduate level. So there are important hurdles in introducing geosynthetics into undergraduate education. And I'm going to list a few hurdles that I have identified. The first one, I'm going to call it the curriculum hurdle. And this comes from a fact or a few facts. First, as university educators, and I'm one of them, we're facing an increasing challenge and a vastly expanded technical base. Now, if you are not an educator, you may not necessarily realize how hard it is to introduce, particularly at the undergraduate level, new topics into our curriculum. And there is good reason for that. So we are posed as educators in engineering, in civil engineering, with a dilemma posed by the need to limit the range of materials that we need to cover, but at the same time meeting the needs of young engineers that with the material that they will need when they face the profession. So this, even though this is a dilemma, that doesn't mean that new material cannot be incorporated into the curriculum. It's tough, but it should be done if necessary. And let me tell you my view, and this is my personal view of what is the status of this, what I called the curriculum hurdle. My view is that there is a growing consensus within the engineering community, and again, we're not talking about the geosynthetics community. We're talking about the civil engineering community, a broad community, that geosynthetics constitute a comparatively new technology, but that civil engineering professionals will face this technology very early in their career, and consequently, they should be introduced at the undergraduate level. And this is good news, or at least it's good progress, at least in relation to what it may have been 10 years ago. But there are more hurdles. A second hurdle, I would call it the reach hurdle. How many young professionals at their undergraduate level can be addressed, can be exposed to geosynthetics? And our consensus, at least within the geosynthetics community, there is a clear consensus that all undergraduate civil engineering students need to be exposed to basic information on geosynthetics. Not a small group of them that end up taking a technical elective, but all civil engineering students. And even if this means that all of the students take perhaps just one single hour of a class on geosynthetics offered at some point during their 4-year program. This may seem very achievable, just 1 hour, but it's not, because we're saying 1 hour to all undergraduate civil engineering students. The status of this, I would say, that is unclear. It's not clear to me how well we are accomplishing this or handling this important reach hurdle. Third hurdle is the faculty readiness hurdle. I would say that engineering professors themselves, we ourselves, have not been exposed during our training as engineers to the basics of geosynthetics. The status of satisfying of overcoming this hurdle, I would say, in my opinion, that is improving. And my last hurdle, and probably the one that I'm going to focus the most today, is what I'm going to call the didactic hurdle. And that is among the various topics that we professors need to teach, need to address. Geosynthetics is particularly broad. The breadth of geosynthetics is a good thing, but to teach a broad topic such as geosynthetics poses a clear challenge. So I would say the status is that if we think about it, if we manage it properly, if we carefully integrate geosynthetics concepts into the previously delivered content, this can be achieved. And in order to show you some about this, let me give you an example. And again, we're talking about teaching geosynthetics at the undergraduate level. This is a very important, well-identified goal within the geosynthetics community that is understood, and there's consensus that should be a priority. So let me give you some teaching samples at the undergraduate level on how this could be addressed. And I'm going to give you my own experience in this. So I'm going to, in the next few slides, I'm going to show you a few slides that illustrate how I would introduce to my undergraduate students in a single hour lecture that I have about geosynthetics, this one important topic. And I do it within the context of a class that is a Introduction to Geotechnical Engineering. There may be more classes on geosynthetics beyond the one that I'm going to show you, but they are at the what we call upper level undergraduate courses, and these are not necessarily taken by all civil engineering students. So I'm going to show you the curriculum of one class on geotechnical engineering, Introduction to Geotechnical Engineering, that is taken, why we chose this class, because this is taken by all civil engineering students. No civil engineer student, at least in my university, will graduate without taking this class. And here in red is types and functions of geosynthetics. And you can see how hard it is within 30 hours lectures to introduce geosynthetics in a curriculum in which we're competing with learning how soils classify, learning Darcy's law about hydraulics of soils, learning consolidation, shear strength, and the basics of some geotechnical engineering design. Very, very tough competition among very, very important topics. And this is the reality that we are faced on how to handle the teaching of geosynthetics, a particularly broad subject matter. So let me give you some slides that illustrate this. And I typically would link, this is the beginning of my class, and I'm going to tell you, okay, this 1 hour, I'm going to tell you everything that you can learn about geosynthetics, perhaps the only 1 hour that you will be exposed to geosynthetics in your entire 4-year curriculum. And typically, I would start by linking the geosynthetics that we're going to introduce to the different types, other types of geomaterials, gravels and sands and silts and clays. And now we have a new geomaterial. It's a geomaterial because we're going to use it in geotechnical projects, but it's not natural, and still it's a geomaterial, and we need to introduce it, and this is the topic of this one class. Typically, I would then challenge the students to recognize, for example, what is in this picture. I'm not sure if you would know what this is in this picture, and it's typically, I would get very creative responses, but what happens is that this one picture is one of the relics of the Great Wall of China. This is in the Han Dynasty in the Great Wall of China. It is not the Great Wall of China as many of us may recognize it in the area of Beijing, that's 400 years old. We're talking about these relics that are 2,000 years old, over 2,000 years old. And here I bring the concept of a technology, in this case using fibers, natural inclusions into the soil that will lead to a very long-lasting infrastructure, geotechnical infrastructure. And then, without further ado, I will introduce my students to the wide range of geosynthetic types. And typically, I would tell them what the name of the geosynthetics are. This is a crash exposure to many new terms. And then I will come back to each one of these terms with a few pictures of each one of them and with a few key concepts of the geotextiles and geogrids and geomembranes and geonets. And then I do a particular link to the types of geosynthetics and to the functions of geosynthetics. And this is where the link with everything that the undergraduate students in an introductory class to geotechnical engineering, this is the opportunity to link the material that they have learned with the material that I will present them with when talking about geosynthetics. Because if you think about it, many of the concepts, the hydraulic concepts, the strength concepts, the material properties concepts, the physical characteristics are a good link between those of geosynthetics and those of soils, other earthen geomaterials that have been exposed. And this is when I introduce first by listing them and then by going one by one to the different functions of geosynthetics. In this case, red mechanical functions and blue hydraulic functions, and the protection is another group of functions. And this is where I will take on making the link between what students have just learned in the few previous classes, the relevant soil properties as soils. Geosynthetics have relevant physical properties, and here are the relevant physical properties that students have been exposed for soils, and some relevant compositional properties. In this case, they will be polymers, other compositional properties for soils, and hydraulics. Here are the parameters or the properties, and that are very highly related to the functions that students have been exposed so far, and the mechanical properties of soils and how they will mimic, in some cases, the properties, the mechanical properties of geosynthetics. It's a tough challenge to introduce this breadth, the broad range of material types and of functions, wide range of functions of geosynthetics in 1 hour, but doing it carefully and integrating the new knowledge with the knowledge that has been presented previously, I think that it can be done very successfully. Let me just make a brief parenthesis in this case to tell you about a marvelous, wonderful resource. If you are an educator, that is available from the IGS. That is the program called Educate the Educators that focus specifically on undergraduate education. This attempts to address one of the concerns, one of the hurdles that I just mentioned, which is the faculty readiness hurdle, because many of us professors have not been exposed during our own education to geosynthetics, and this is addressed by providing fellowships to professors, geotechnical engineering professors, other civil engineering professors, covering travel expenses, providing educational materials. And this is also at the IGS level, this is a great opportunity to integrate the efforts of the IGS at the international level, the national chapters, and industry leaders from each country. So if you are an educator and you're interested in this program, you need to do just one thing: call your IGS chapter representative, and or if you're a leader in your chapter, definitely this is something that you can do. There are additional resources, not only for the Educate the Educators program, but other educational initiatives that the IGS Foundation, a new branch of a separate but integrated with a mission of the IGS, can provide some resources. And the IGS Foundation is always keen to listen about initiatives on education. All right, but back to our topic, which is essentially we're dealing with a challenge, a hurdle on teaching geosynthetics, that is their breadth. I just show you one example, not the only way, but one example of how this can be addressed at the undergraduate and the early exposure, early education on geosynthetics. Let me tell you a little bit about the advanced education of geosynthetics, how this breadth could be addressed or needs to be addressed. It cannot be an afterthought. That's my message here. The breadth of geosynthetics cannot be an afterthought when we are dealing with education. It needs to be purposefully addressed at the early education level and also at the advanced education level. So here is again the didactic hurdle on the advanced education on geosynthetics, and is again the breadth of geosynthetics. It remains, even though without the pressure of having to give everything in 1 hour, but it remains an important educational issue. And I would say that and this is my take on the status of this hurdle at the advanced education on geosynthetics, I think that this can be addressed. However, effort should be placed on explicitly recognizing the breadth of geosynthetics as an important issue and also avoiding generalizations. So I'm going to give you 2 examples that I personally on how I personally, in my teaching of geosynthetics, address this hurdle, the didactic hurdle that is posed by the breadth of geosynthetics. And I'm going to give you 2 examples. Example number 1 is going to be the breadth of geosynthetics when I teach waste containment design. And this, I do not teach a class on geosynthetics. I consider myself an expert on geosynthetics, but at the graduate level, I do not teach a course on geosynthetics. Instead, I teach a course on environmental geotechniques in which I introduce geosynthetics, the environmental aspects, the barrier containment aspects, and I teach another course on earth retaining structures in which part of the course is on geosynthetics. I'm going to show you about how I introduce the breadth of geosynthetics when talking about waste containment design. And this is from a graduate course that I teach at UT Austin. And then I'm going to tell you about the breadth of geosynthetics in roadway design. This is also advanced education, but not at the university level, but at the professional level. This is based on my experience in teaching a roadway design course with my good friend and colleague, Professor Errol Tutumwer. So let me show you the first example. This is, by the time that we get to this topic, geosynthetic barriers, my students at the graduate level have already gone through regulations on waste containment facilities. They have gone through design of clay liners, properties of clay, behavior of clay. They have gone through flow, including the very complex or comparatively complex topic of unsaturated flow, unsaturated salt barriers, and then we get into the topic of the design of barriers, but in this case of geosynthetics. And this is my crash exposure. But by this time, I have already given perhaps 1 or 2 lectures on the ABC on geosynthetic types and geosynthetic functions, but not within the context of design. So this is my first lecture on geosynthetic design of geosynthetic barriers. And it's essentially, I could tell the student, well, here's the skeleton, the earth and skeleton of a waste containment facilities with, here you may recognize, maybe you cannot see my pointer. here is my pointer. So you may recognize the base liner, a compacted clay liner, and you may see here what appears to be a drainage collection system, a leachate collection system at the bottom of a landfill. I also introduced here the use of earthen materials in a groundwater well and in a liquid extraction well. Okay, but in addition to these earthen components in a waste containment facility, a modern landfill will have a number of infiltration barriers, geosynthetic infiltration barriers. And here you see infiltration barriers in the cover system. This happens to be a composite liner. This happens to be a geomembrane with a GCL and a double composite liner as the primary and secondary base barrier systems. But in addition to these earthen components and these yellow infiltration barriers that happen to be geosynthetics, we have actually, these are my examples on the type of products, geosynthetic types that the students have just been exposed to, geomembranes and GCLs. But in addition to these yellow infiltration barriers, we may have many other geosynthetics, including these green reinforcement layers, and we may have reinforcements in the cover system. And notice the relevance here. I will expose the students on the potential use of geosynthetics such as geogrids for stability of the cover system, and differently than also a geosynthetics, perhaps a geogrid or a geotextile, high-strength geotextile, but in this case, under the liner for breaching a void, and potentially also using this green reinforcement geosynthetics for stabilization and for stability of many of the components in our waste containment facility. But and here we have geogrids. For example, of one of the materials, but in addition to the yellow, to the brown earthen materials and the yellow infiltration barriers and the green reinforcement barrier, we have these blue geosynthetic drainage layers. And we have the drainage layer that we place on top of our cover barriers, and on top of each one of the two components of our double composite liner system at the base. And finally, in addition to the brown earthen components and the yellow barrier components and the green reinforcement components and the blue drainage components, and the blue drainage components include geonets and geocomposite drains, we have the purple separation and erosion control elements that complete our big exposure to the presence of geosynthetics in a waste containment facility. All right, and this is an example of how to recognize the breadth of geosynthetics way up front before we jump into the design and the characteristics of each one of them. And also, let me show you an example on how to recognize the breadth of geosynthetics in roadway applications. And essentially, I'm very upfront. I could say that when using geosynthetics in roadway applications, we have some very good news and many, many good opportunities to introduce geosynthetics and improve the performance and the cost and the sustainability of roadways, because, and I'm going to read it, there is a huge number of geosynthetics with a wide range of properties that can be used in numerous roadway applications to fulfill many different functions through a large variety of mechanisms. This is great news. We can make excellent use of all these different alternatives on using geosynthetics, but there are some not so good news, and you can read it by yourself. So the same thing that makes it a good news, the wide range of geosynthetics and properties and applications and functions and mechanisms can become a problem if we do not understand them properly. And here we are again, the geosynthetic functions in roadways applications and how this wide range and the breadth of geosynthetics can be explicitly addressed by carefully indicating each one of, in this case, they are the different functions, and both mechanical functions and hydraulic functions, and how they can all be integrated into, in this case, the structural package of a roadway. And it becomes even more complex in the sense that the breadth is not only on the functions, but is also on the applications on roadways, from applications on top of the roadway, mitigation of reflective cracking, structural asphalt overlays, all the way here going through applications 2, 3, 4, 5, 6, in which case we're at the subgrade level, applications that we can use, in which we can use geosynthetics to improve the characteristics of the subgrade. And then we have the design objectives, and eventually we need to make it, the functions are the gateway to the properties that we need. And what the design engineer needs to do is to go through the objectives to the applications. We need one more step. In order to make it to the functions, we need the mechanisms, and then the functions, and eventually the properties. So even though when geotechnical engineers or transportation engineers face the potential use of geosynthetics, they do it through the gate of expecting a certain application because of certain design objectives. We need to integrate the breadth of knowledge that we have of different material properties and different functions and the different applications that we have on geosynthetics. Okay, so I have told you about one challenge as educator of geosynthetics, which is the geosynthetics breadth. But we have an advantage when we teach geosynthetics, and this also should be recognized when addressing when facing geosynthetics as educators, which is an appeal that geosynthetics present. And that appeal is their ingenuity. And let me illustrate with some case histories very shortly what this means, why ingenuity on geosynthetics and versus the typical ingenuity that we may also have in other areas of civil engineering, geotechnical engineering, but I think that it makes it particularly when designing infrastructure with geosynthetics, ingenuity can be a mark, a classic, a common aspect in the design. And let me walk you through the ingenuity in the use of geosynthetics in infrastructure in multiple, not one, not two, but 10 different areas of geotechnical engineering. And that includes earth dams. And I would tell you, for example, the ingenuity and the design of a very classic case history, the Valcroze Dam, designed in France. This happens to be the first dam designed actually by J.P. Giroux, in which the reason why this was selected is because critical components of the earth dam, in this case, the filters were not readily available, granular filters. And so geotextiles were identified to satisfy the multiple filter criteria. And here we have a picture of the incorporation of geotextiles for the first time in this design and in the construction. And even though this happens to be the first one, it has been subsequently evaluated, and actually there were recent re-evaluations of the use of filters in this historical case history. And here it is constructed in the 1970s. It was a homogeneous dam. Non-woven geotextiles were used, but through the continuous evaluation and re-evaluation, it has been observed that the performance of the drain has been satisfactory since its construction. As part of that re-evaluation, because Dr. Giroux confessed that the Valcroze Dam had been selected without the existence of a thorough design method. However, the re-evaluation of the dam, of this filter, than actually on the occasion of Dr. Giroux's Terzaghi's lecture, concluded that the internal stability had been appropriate, and that justifies the reason and validates the rationale on why the performance of the Valcross dam had continued to be satisfactory. So now it turns out that granular filters, after studying these geosynthetic filters, new aspects in filter design came to light, including those that may have been overlooked in the design of granular filters. So the use, for example, the use of retention criteria that was developed for geotextile filters may resulted in the improvement in the design of granular filters as a consequence of, in this case, history and subsequent studies. But in addition to earth dams, the ingenuity of geosynthetics is also present in the design of resisting barriers. And to show you an example, I'm going to take you very close here. At home, I'm in Austin, Texas. In San Antonio, Texas, happens to be the location, the location where alternative energy in landfill closures was implemented by using a very ingenious new type of design, something that we may have never anticipated perhaps 10, 20 years ago, which is having final closures with a design that incorporates in their design exposed geomembrane covers. And by doing so, this facilitates the incorporation of solar panels that were particularly suitable for the synergism that the use of exposed geomembranes provide. Now, it turns out that there are important elements in the design that should be addressed, particularly when designing exposed geomembrane covers. Wind uplift is a particularly relevant design consideration, but it was very rapidly installed. It was particularly straightforward. These were flexible solar laminate panels. It happens to be the first solar energy cover in the United States, but there are now many additional and newer ones. And here's just an example on the trenches adopted during the construction of the Testament. This is the name of the landfill, the Testament landfill in San Antonio. Essentially, the main aspect was on how to incorporate, to provide anchor to prevent the wind uplift of the exposed geomembrane. What is the significance of this ingenious design? Well, the design of the cover systems involving exposed geomembranes became particularly attractive when implementing projects, closure systems that incorporate the generation of alternative energy. But it was not only in earth dams and resistive barriers. I'm going to give you an example of the use of geosynthetics on what we call unsaturated salt covers, where, and this is the case of the Rocky Mountain Arsenal near Denver, Colorado. And the challenge in here was a wide, very, very vast area, a contaminated area, contaminated soils. And the target was to create in this area, if you fly to Denver, you're going to see from Denver to downtown Denver, you're going to drive, and you're going to see a very not developed area. Really what you're driving by is by the Rocky Mountain Arsenal, but it has been now transformed into a first or largest urban wildlife refuge. How? By designing a cover system that incorporated a geosynthetic capillary barrier within the unsaturated salt system. And this is a very, very large area. This is 37 square miles. Originally, one of the square miles, section 36 of the Rocky Mountain Arsenal. This is where the Army initially started developing a chemical weapons program, and then insecticides and many additional chemical industries were developed in this area. This is during the during the closure of the site. Sarin bomblets were even identified during this period. And let me show you there were many elements in the design. I'm just going to show you one of them, which is the final cover design for the closure of the contaminated soils that actually most of the hazardous waste had been consolidated into on-site hazardous waste landfills, and this is the closure of what remained as the contaminated soils, the superficial soils. But the important aspect in this design that I would like to call your attention is that geotextiles, non-woven geotextiles, were incorporated into the design as capillary barriers in the final cover systems of unsaturated soils. And then I'm going to walk you through a fourth geotechnical engineering field, which is the veneer design, stability design. And this is another case of a waste containment facility. In this case, I'm going to take you to Los Angeles for stabilization of steep, long covers of waste containment. And in a seismic area, in this case, geosynthetic reinforcements were adopted in this particular case by anchoring them into solid waste. And here we have a view. If you know Los Angeles, this is highway number 7, the Pomona Highway. And when you drive by the Pomona Highway, you're going to see many. They look like mountains. They are not mountains. They are waste containment facilities. This happens to be very steep slopes of a tall facility, hazardous waste containment facility, including there was an attempt, one of the potential solutions on how to provide stability to this area was by using exposed geomembranes. It was suitable solution, but it was not accepted by the neighbors, by the community. But reinforcement was adopted by anchoring the horizontal reinforcement layers into solid waste. Let me take you to a fifth case. In this case, hydraulic protection. I'm going to take you now to a mining site in Las Bambas copper mine near Cusco, Peru. In this case, there was a need of rapid mining. Everything needs to be fast, and this was not an exception. Rapid relocation of water water from a reservoir for mine operations. So this led to the use of a high capacity canal using geocells with concrete infill. Here's a view of the mining site, the operations site, and this is the location of the reservoir from where water had to be transported to the source of the water to be transported to this new location. And they going through a very difficult terrain where at an average altitude of 4,000 meters above sea level. So when the engineers had to relocate water from this location to this location. The ingenious design in this case was the design of a very high capacity canal, but with essentially vertical side slopes. And the way in which this was addressed was not only by the use of geocells, but geocells that had to be attached to geogrids. And the infill was concrete, but it was provided by shotcrete. This allowed rapid construction, very effective construction of a highly efficient canal. And here's a view of the site during construction. So what is the significance of the ingenious design? The use of geocells with concrete infill actually has become more and more accepted in the design, in this particular case, in mining applications, certainly in the area of Peru. 6, we went through earth dams and resistive barriers and unsaturated soil covers and veneers and hydraulic protection. Let me take you through an area where we typically do not think of geosynthetics, which is foundation engineering. And yes, geosynthetics can be used in foundation engineering. In this case, I'm going to take you to Turkey on the design of an embankment founded on very soft soils underwater and in an area of high seismicity. And very significant challenges, and in order to address them, geosynthetics were tapped into. And this was in the form of geotextile encased columns. And here you have a view of the embankment, 22 meters high embankment, over 400 meters long, and it was subjected to a high seismicity, 40% of the acceleration of gravity. And in this case, even stone columns could not be adequate because of the very low shear strength on the foundation soils. And here we have some views of the construction. 200,000 meters over 12,000 geotextile encased columns were adopted in this particular site. The evaluation that was conducted regarding the suitability of the solution under seismic conditions was particularly beneficial toward the selection of geotextile encased columns, and this was a very successfully implemented and highly monitored. And after these 6 areas of very different areas of geotechnical engineering, let me take you to another one. Also with a great use of tapping into the ingenuity, in this case, the design of bridge abutments. A big problem in the design of bridge abutments is the bump at the end of the bridge caused by differential settlements between the foundation of the bridge itself and the foundation of the approaching road. How can be used by a new technology that I'm gonna identify it as load-carrying geosynthetic reinforced bridge abutments. And this is the case of the Founder's Meadows Bridge near Denver, Colorado, that was constructed. Look at this structure. This was built over 25 years ago, and it continues to look perfectly fine. And what it is important in this particular structure is that the way that the structure was founded. Typically, we see many reinforced walls when in abutment walls, but this is typically the cross-section, a typical cross-section of those abutments. The load of the bridge is carried of the foundations through deep foundations, and the load of the approaching road is transferred to the foundation through a superficially founded MSE wall in this particular case. Unlike this conventional, this is a GMSE wall, geosynthetic mechanically stabilized earth bridge abutment. Unlike this is what we call a load-carrying geosynthetic bridge abutment. This was constructed very rapidly, and it has performed excellently without any signs of differential settlements of the bump at the end of the bridge, even after 25 years. Let me take you to another achievement within geotechnical engineering using geosynthetics, retaining walls. This is the Sikkim Airport. It was designed, what I understand is the tallest geosynthetic reinforced structure in the world and in the seismically active area. How it was designed by using geosynthetic reinforcements. Very difficult design could be achieved because of the ingenious use of geosynthetic reinforcement. And in the Indian Himalayas, seismic considerations was an important aspect in the design. The use of locally available backfill was an important aspect in this structure. And here we have a picture, but it's so hard to take a picture of such a tall structure. What you're seeing here are 3 of the terraces in this particular structure. What you do not see here is that there are 2 additional terraces going below what you can see in this picture. And actually, this was a picture taken during construction on this very massive structure that constitutes today probably the tallest geosynthetic reinforced structure in the world. And I took you through 8, but that's not all. We also have 9 embankments. In this case, I'm going to take you to the Idaho National Forest, where steep slopes had to be constructed, but using backfill with comparatively high fine percentage of fines. And this was achieved by using what we may call dual function geosynthetic inclusions. These geosynthetic inclusions would work not only as reinforcements, which we need for stability, but also as in-plane drainage layers, which will facilitate also improve the stability of the structures. And this was done. Here's a view of the construction of the geotextile reinforced soil slope, in which an important element in the design was the use of the geosynthetics, ingenious use of geosynthetics, not only as reinforcements, but also as lateral drains. And let me take you to my 10th case, and I'm going very quickly because my intention is to show you that geosynthetics are being used in so many areas of geotechnical engineering, in this case in roadway design, in which the concept was to minimize the detrimental effect of roadways founded on expansive clays. How it was done by using geosynthetics to stabilize the base of the roadway, to provide a ductility to the system, because one of the main problems when founding roadways on expansive clays is that during the dry season we will end up with a very characteristic problem, which are the longitudinal cracks. They have nothing to do with the traffic loads. They may even close partly, but they're not sealed during the wet season. And here we have an example in this particular case in Grimes County in Texas, where we have a road, multiple sections, some of them stabilized and some of them not, control sections. And seeing is believing. Here we have a geosynthetic stabilized section without longitudinal cracks and a control section with the very characteristic fingerprint of the distress of roadways on expansive clays, which are the longitudinal cracks. So in summary, when it comes to an appeal of geosynthetics for the design of structures, geotechnical structures, I hope that I conveyed that these were illustrations, but those are not exceptions. There are so many cases in which geosynthetics could be used with ingenuity in the design of, in this case, 10 different areas of geotechnical engineering. Earth dams, resistive covers, unsaturated soil covers, veneer slopes, hydraulic protection, foundation engineering, bridge abutments, retaining walls, embankments, and roadways. Which brings me to, these were two important lessons that I would like to convey regarding the teaching of geosynthetics. One is their breadth, which should be recognized, but an important appeal, which is the ingenuity that the use of geosynthetics can bring to geotechnical design. So let me take you finally to the power behind learning geosynthetics. So teaching, which is what I focused so far, can only be deemed successful if it leads to a successful learning experience. So if we have a successful teaching and a successful, which means a successful learning experience, because of the breadth of geosynthetics, we expose young engineers, professionals, to valuing, particularly being trained to value for the careful assessment of alternatives to eventually select what could be or what may be the best engineering choices. Precisely because of the breadth of geosynthetics is that we are forced to make the assessment of alternatives and explore different choices. Because of the ingenuity of geosynthetics, I think that we're particularly trained to a successful creativity and discovery that we are forced to because of the many choices that we have, because of the ability that we have with geosynthetics, which is not an ability that we may have with many other materials, to tailor the properties that we need for design. And in order to make my point regarding the power behind the learning of geosynthetics, I'm going to tap into the two quotes. One by Professor Marina Pantazido. She's a professor at the National Technical University of Athens, and she happens to be the chair of TC 306 from the International Society of Soil Mechanics and Geotechnical Engineering, the chair of the Technical Committee on Geotechnical Education. She happened to be the chair of the 5th International Conference of Geotechnical Engineering. And to make the case on how powerful the learning of geosynthetics may be, I will ask you, I will ask you to read by yourself what Professor Pantazido had to say. And in addition to this important quote, very powerful quote about how geosynthetics, understanding geosynthetics can help us understand soils, let me take you to another quote. In this case, is a quote by Dr. J.P. Giroux, which is the founding father of our International Society, but I'm gonna, among the many elements that makes him a distinguished scholar, I'm gonna take you to his distinction as a 53rd Terzaghi lecturer, because which is somewhat related to the Valcross Dam case history that I just mentioned, because this is a quote that comes from the study that he did on understanding the performance, on the mechanisms and the requirements for geotextile filters. And this is his quote, and I'm going to ask you to read him. Very important concepts on technology transfer, but not only from geotechnical engineering to geosynthetic engineering, but now coming back. That is the power behind learning geosynthetics. Ultimately, perhaps, and ultimately, the power behind learning geosynthetics may stem precisely from what it is a challenge on teaching it and on learning it, which is its breadth, but what is also its appeal, the appeal of ingenuity, because probably this leads, learning geosynthetics trains us to make good technical choices and to foster creativity. And as mentioned by Professor Pantazido and Dr. Giroux, we are trained by learning geosynthetics on making good choices and foster creativity, but not only on geosynthetic projects, but as geotechnical engineers or as engineers at large. And with that, I thank you for your attention and happy birthday, IGS.
Jorge, thank you very much for the very insightful presentation. That's and thank you for the wishes to the IGS. Jorge, I see we have exactly 1 minute to go through the question. I do have 2 questions, so I'm gonna ask you to try to be short in your answer, try to go through. I think the very insightful question. The first one is from an anonymous that asks, what is the issue with maintaining the use of geomembranes for sanitary landfall? And what would be the recommendation to prevent tearing during the operation, considering that the project is located in a rural area in a country in Central America? So I think you talk about teaching and designing, but this is a very important question of how the installation and the operation of geosynthetics.
Well, I will not get into the details of this, but let me tell you one thing. Some decades ago, the first question that we had when installing geomembranes was, how long will they last? And this issue has been addressed. It was a very fair question, but this issue is being addressed more and more, and we know that they will last very long. But however, the very important issue today in terms of the performance of waste containment facilities is quality control during installation. And this is a very important issue. And there are many advances But we start by recognizing, as you probably did, that this is a very important issue, and there are important protocols for quality control and quality assurance in the installation of geosynthetics, in particular geomembranes.
Indeed, indeed, Jorge. And I think I want to piggyback on what you were saying, because your second question from Marina Pentazidou is, I thought that geomembrane are not resistant to sunlight. Is this green geomembrane a special sunlight resistant geomembrane?
Well, that is true. But the fact is that the geosynthetics in general, but geomembranes in particular, their formulation has advanced so much that while ultraviolet degradation continues to be a very, very important issue, they will last long enough that they can be adapted for permanent closure, and permanent closure has a design life of exposed geomembranes. This is a reasonably, I'm going to call it recent development, but it has been recognized. Many exposed geomembrane covers are being designed for waste containment facilities for mining operations as well.
Okay, thank you. I think we 2 minutes over time, so I would like to close the session. I really thank you. I know that you are a very busy professor teaching geosynthetics, so we don't want to take further of your time. It was a great pleasure having you. And if we get any other question about your lecture, we'll pass them on and then we'll share the recording. So with that, thank you everybody for joining. I'll just remind you that this was the first day. Tomorrow there is a second day, and Wabelu is going to talk about geosynthetic in China, history, manufacturing, application. And, oh, sorry, that's Wednesday. Sorry, you see, very busy schedule is David Shercliffe and Kasia Zamara talking 40 years saving the Earth. And that will be tomorrow, 7th of November at 1300 UTC time. And then following the Ask the Officers with our treasurer, Professor Gian. Thank you, everybody. Thank you, Jorge, once again.
Thank you, everyone.
Great day. Bye-bye.